So your question is how to determine how I decide what angles I'm using. Is that correct?
Exactly, yeah.
Or how I decide if I'm
Okay.
using. So this was for like a hanging sign thing. Or something like that. And you can be given the angles in a couple of different ways. Sometimes they'll give them to you here, or sometimes they'll give them to you here. So actually, let me do those two different colors so we can talk about how we can distinguish both. There we go. So starting with here, and I'm just going to label this like alpha and beta instead of giving it numbers. If I do a free body diagram, for both of them, I have straight down as the force of gravity from that sign. And then going up, no matter which angle I'm using, I have this force of tension going like that. Let's go darker. The force of tension that goes straight up that line that's attached to both. So we can label that like tension 1 and tension 2. So the important part of breaking these guys down into vectors is to see that this piece, everything coming down here, is your y-axis. So if I wanted to, I could do something like do kind of a drop dotted line. Ooh, you know what? I want a ruler. This will do. Just so it's a little bit neater. Oh, come on. So that would be my y-axis. And then this would be my x-axis. I'm really good at drawing on the other paper. Okay. So this one is pretty easy to see. I want anything that is up and down on this y-axis to go with that force of gravity. Are you good with that?
Yep.
Okay. So if that's the case, then for the y, I want the down piece. If I look here, this is coming down. So I'm going to have like a vector coming out like that and then going straight up. And it doesn't matter where I draw it. That is going to be the y piece, so that tension 1 in the y. And then the same thing over here. If I come over here, the piece that is parallel to the y-axis is going to be this guy coming straight up. Are you good with that?
Yeah, so tension 1y and tension 2y.
Yep.
So that's perfect.
Okay, so then the next one is for the x. So I'm sorry, let me back up 2 seconds. The one thing I want to point out here is that because this thing is hanging, it's in equilibrium. So if it's in equilibrium, it's not accelerating, that means the sum of these two tensions must equal the sum of that gravity. So this force coming down is going to be equal and opposite of the sum of these two going up. Do you see that?
Okay. Yeah, so must equal the sums of both the tensions together?
Yes, of the two pieces that are going straight up.
Okay.
Okay, so this is on axes in the y. These are both on axes in the y. This is, I'm sorry, this is the piece of the tensions in the y going straight up. So the other piece that we don't have yet then would be, this is the line going up. Well, there's going to be a component of tension in the x for both. One, sorry, I labeled it differently. And then this one is the same thing. It's got a component of tension from that line going straight out like that. Tension 2 and the x. So what I know from my forces, again, because it's not accelerating up or down or left or right, is that these two components have to be equal and opposite. So these two things are going to cancel out to keep this thing in equilibrium towards not accelerating or moving. Are you good with that?
Yep.
Cool. So now the second part, and you said you were good with that mnemonic SOHCAHTOA?
Yeah.
Oh, that's an A. Almost. So the key thing here is this is just my hypotenuse for both of these triangles. So this is the H for the hypotenuse for both sine and cosine. And so wherever the angle is that I have, then I can use that angle to decide which one is my adjacent piece and which one is my opposite piece. So looking at the alpha, if I look at this, I'm like, okay, so for the x piece, what do I have? Well, the tension in the x is touching that alpha angle. So I would have tension 1, which is this whole vector here, times touching cosine adjacent, so cosine of alpha. And in the y, well, that's the opposite vector from this angle. It's looking out at it. So this is going to be the total force vector, so this tension vector, tension 1, times sine of alpha. Another way to do that, what I'm doing in my head is I'm saying so cautoa, so sine of alpha equals opposite over hypotenuse. So opposite would be tension 1 in the y over hypotenuse, which is just tension 1. So tension 1 times sine of alpha gives me that tension piece in the y. Are you good with that?
Mm-hmm.
You have any questions on that?
Let's see. So, all right. So tension 1 will be equal to the hypotenuse because it's at that angle.
Yeah, yeah, because the vector isn't straight up or down on the axes. So this is my total force vector, but it's at an angle, so it has a piece in the x and a piece in the y.
Mm-hmm. And is it safe to say that when regarding x, it will always be cosine and y will always be sine?
No.
Or it just depends? No, okay.
It depends. Yeah.
But depends. All right.
Yeah. Yeah, and which one is it? When we do forces pushing things down, when they come out the other side, yeah, it depends on where you're taking the angle to, right? So if instead of this picture, let's do one that shows that it's not always. Instead of this picture, if I go something like this, and this time, if I gave you this as the angle, so if I call that alpha and that beta. So again, this is my tension vector going straight up. I want a different color. It stands out. My tension vector going straight up. So on this one, my y component, we can see, is just straight down the middle going up. Because again, my force of gravity, I can remind myself that that is just pointing straight down all on the y. And so I have a piece of tension coming up from both of those guys. This would be 1 and 2. It's just combined. They're both in the same spot. And my x piece then is coming out like this and coming out like this. So if I call this tension 1 and tension 2, then this is tension 1 in the x, and this is tension 2 in the x. So now going back to our mnemonic, and I look at this, here's my angle. Now my x component is the opposite side.
Oh, yes, I see.
Yeah. So I would have, let's see, sine, so tension 1, sine of alpha, then equals my tension 1 in the x. You see that?
Makes sense. Mm-hmm.
Yeah, so
it totally depend on the, yeah.
Yep. And the question you asked, and the reason why I emphasize that is this becomes an always habit, and it bites people in unpleasant ways when they don't expect it. When things are given in different locations, and then you start using this as like cosine is always x, and then you're like, I don't understand why nothing is working.
Mm-hmm.
But that's it. So if you just always, I mean, you just look at this angle, and the adjacent side is whatever x or y piece is actually touching that angle. And then the opposite side, you can think of it as an eyeball, just looking at this line here. It's opposite of the angle in question.
Mm-hmm.
And then when we're talking forces, this hypotenuse is always going to be that specific force. It's just going to be like, this could be a push or a pull or a tension or gravity or the normal. It can be any number of things off at an angle, and then we can just break it down into its x and y's.